Intrigued? This is a remnant of supernova 1987A. While we universally recognize this brilliant display of gas and light as an explosion, we often misunderstand exactly what we're looking at. The optical event we observe from Earth trails the primary explosion as a delayed thermodynamic echo, arriving hours after the initial catastrophe in the star's center. When we compare the physical remnant to the raw, plotted data of a light curve, we see a specific geometric pattern, a sharp, brilliant peak in magnitude, followed by a long, sweeping exponential tail. To understand the high-energy physics governing this curve, we must discard surface-level observations and look deeper into the star's interior. Two distinct mechanisms drive these deaths: the runaway thermal fusion of white dwarfs and the sudden gravitational core collapse of massive stars. By reading the exact shape of this light curve, astrophysicists can reverse engineer the mass, the core physics, and the specific radioactive isotopes forged during the star's final moments. We are moving past the flash of light and learning to read these events as a forensic, thermodynamic blueprint of stellar death. Early astronomers relied on a single observational metric to classify supernovae: the presence or absence of hydrogen absorption lines in the star spectrum. This produced a rigid historical taxonomy. Any event without hydrogen was labeled Type 1, while those with visible hydrogen became Type 2. Basing a classification strictly on surface chemistry fails to describe the actual physical mechanism of the explosion. We have to rebuild this system based on physical reality, splitting supernovae into thermal runaway events and core collapse events. Thermal runaway, or Type AA, occurs when a dense carbon-oxygen white dwarf siphons plasma from a companion star. The detonation occurs at the Chandrasekhar limit, roughly 1.44 solar masses, triggering runaway nuclear fusion that destroys the star. The opposing mechanism, core collapse, happens when a massive star exhausts its nuclear fuel and implodes under its own gravity. This creates a taxonomic anomaly. Type IB and IC supernovae lack hydrogen, yet they are actually massive core collapse events, not white dwarf detonations. Their hydrogen envelopes were stripped away by binary companions or powerful stellar winds prior to the final collapse. Focusing on thermodynamic reality reveals the fundamental core physics that spectral taxonomy often obscures. To see this mechanism in action, we need to focus deep inside a massive star in the seconds before it dies. The star's interior consists of onion-like layers of fused elements, all pressing down on a central core of dense iron. Iron fusion marks the end of the line. Because it requires more energy than it yields, outward radiation pressure simply vanishes. For a brief moment, electron degeneracy pressure holds the weight. Then gravity overcomes it. The iron core collapses at nearly 25% the speed of light, crushing protons and electrons into a neutron core just 30 kilometers wide. Infalling stellar material strikes this incompressible core and rebounds violently outward, creating a shockwave. We quantify this energy using the Pho, equal to 10 to the 44th joules. By tracking output in phos, we see exactly where energy goes. Kinetic energy reaches 1 Pho. Visible electromagnetic radiation is 0.01 phos. Neutrino output, however, skyrockets to 100 phos. In just 10 seconds, the star converts 10% of its entire rest mass into a flood of subatomic neutrinos. But the outward shockwave quickly loses energy. It stalls, threatening a total collapse into a black hole without a visible explosion. 3D supercomputer simulations show that turbulent neutrino heating reinvigorates this stalled shock, finally blasting the star apart. Because 99% of the energy escapes undetected as neutrinos, the visible explosion we see is effectively a thermodynamic rounding error. The reinvigorated shockwave tears through the star's dense envelope. This glowing front triggers explosive nucleosynthesis, forging the heaviest elements in the universe as it expands. The most critical byproduct of this process is the radioactive isotope nickel-56. The optical light we observe is actually the thermalized energy of these decaying isotopes. On our light curve, the drop from the peak follows the decay of nickel-56. Nickel-56 has a 6-day half-life as it decays into cobalt-56. This rapid release of energy drives the brilliant, sharp peak of the explosion. The decay then moves to the next step, cobalt-56 turning into stable iron-56. With a 77-day half-life, this cobalt decay perfectly dictates the long exponential tail of the light curve. Type 2P supernovae offer a unique contrast, showing a prolonged plateau in their brightness rather than a steady decline. The shockwave ionizes the star's massive hydrogen envelope. As that gas cools and recombines, it emits a steady stream of photons, keeping the curve flat for months. This light curve translates the signature of radioactive isotopes forged in the star's dying milliseconds into a readable record, rather than measuring the primary blast directly. In thermal runaway events, the rigid Chandrasekhar limit ensures each white dwarf delivers a nearly identical payload of nickel-56. This consistency allows astrophysicists to use these Type Ia supernovae as standard candles, plotting distance against redshift to map the expansion of the cosmos. A recent controversy suggested that the age and mass of host galaxies might be distorting the brightness of these candles. However, rigorous recalibrations of host environments confirmed the standard candle model is robust, and the previous claims were based on flawed assumptions. This recalibrated data remains the cornerstone of the evidence that the expansion of our universe is accelerating. We are now applying these models to the very edge of the observable universe, using the gold-coated mirrors of the James Webb Space Telescope. Webb recently identified a core collapse supernova from a time when the universe was only 730 million years old. Despite existing in the early, low metallicity universe, this ancient explosion's light curve perfectly mirrors the physics of modern supernovae. From our local neighborhood to the dawn of time, the mechanics of stellar death remain an immutable law, allowing us to read the history of the cosmos in a single flash of fading light.